So the purpose of the experiment was to determine the Ka of an unknown acid, so you could determine what the acid actually was. And we're using two methods, the equilibrium equation method and the partial neutralization of mixtures method. So for the first method, we use the equation here that you're given. Right there. Okay, so what's the initial concentration of the acid? Well, that's already been calculated from the titration, and it's 0.106 moles per decimeter cubed. And the initial concentration of the hydronium ion is 0, and the conjugate base is also 0. Now we've got to work out the change in concentration at equilibrium, because obviously a weak acid does not stay as the weak acid in solution. It's going to form and associated into the hydronium ion and the conjugate base of the acid. So the way we work out the change in concentration is first work out the concentration of the hydronium ion. Okay, so what is the concentration of the hydronium ion? Well, luckily enough, we measured the pH, so it's going to be equal to 10 to the power of the negative pH, which we calculated at 3.2. So it means that the concentration at equilibrium for the proton ion in the solution is going to be, if you plug in the numbers, 6.3 times 10 to the negative 4 moles per decimeter cubed. Okay, so we can plug that in to our equation, 6.3 times 10 to the negative 4. Okay, the important thing to note also is that because it is a weak acid, then we're going to make an assumption. We're going to assume that the concentration of the hydronium ion is going to equal to the concentration of the conjugate base. So the concentration is going to be plus as well. Okay, plus 6.3 times 10 to the negative 4 for also the conjugate base. Right, and obviously it's now the acid has been transformed into this, so you can work out the change in concentration. It's going to change to basically subtracting this value here and this value here, and we're going to have 0.10574. Now, for the purposes of this equation, that change isn't particularly significant. So we're just going to say the equilibrium concentration still remains, at least for the acid, essentially the same, 0.106. Okay, we'll just say it's similar to that. And that means that at equilibrium, the concentration of the protons is going to be 6.3 times negative 4, and the concentration of the conjugate base is going to be the same, 6.3 times 10 to the negative 4. Okay. So now we use the equilibrium expression. The Ka will equal the concentration of the protons, which we know. Okay. 6.3 times 10 to the negative 4. And we can say, because the concentration of the conjugate base and the acid is the same, we can just all square that, okay, and then divide it by the concentration of the acid itself. Okay, so now we have a value for that, and it's going to be equal to, if I get my calculator out, 3.74 times 10 to the negative 6. Okay, so that's our first Ka value, which is going to be equal to the Ka of the acid using this particular method. Okay, so there we go. So we can put it in the Ka, 3.74 times 10 to the negative 6. Okay, so that's using that particular method. That's known as the neutralization equilibrium equation method. Okay, the second method we can now look at is going to be the partial neutralization of mixtures. Okay. Now, I'm just using Nannerel's experiment as an example. Okay, so she did basically what you do is, because you know the final volume of the amount of base that will neutralize the acid at the end point, okay, you're basically dividing up those and doing partial neutralizations. Okay, so you're doing neutralization where you use a quarter of the amount of at neutralization, half the amount of neutralization, and 3/4 the amount of neutralization. So I'm just going to use Nannerel's numbers for this. So her initial burette readings were all 0, 0, 0. Okay, and her final readings were 2.625. Okay, therefore the maths is easy. What you've done is you've just added 2.625 of the base in terms of centimeters cubed. The next reading was 5.250, and that was also 5.250. And the final reading, because I have to write really small, is 7.875 and 7.875. So I'll be using these numbers. Obviously, you will be using different numbers to calculate the asserted values for yourself. Okay, so the first thing we have to work out is work out the concentration for the A minus for the first case. Okay, so just label these 1, 2, and 3. So the first case there. Okay, so the concentration of A minus will be equal to the concentration of the hydroxide, basically, you added. Okay, because remembering we are using this reaction equilibrium here. Okay, so that will be equal to the volume of the hydroxide that has been added times the concentration of the acid, of the base, which is 0.996, which I gave you. Okay, and that will be all divided by the total volume. Okay, so if you plug in the numbers, the volume of the hydroxide will of course come from here, and you have to divide by 1000 because you're converting centimeters cubed into decimeters cubed, and the number we come up with is going to be 0.0207 moles per decimeter cubed. Okay, so the concentration of the A minus. And how do we get the volume, the total volume? Okay, it's going to be basically your 10 mils of acid plus the volume of the hydroxide that you added. Okay, so this will be 12.625 centimeters cubed in this particular example. Okay, so now we have the concentration of the A minus. The concentration of the acid will be more interesting. Okay, so that's going to equal obviously the number of moles of the HA divided by the total volume. Okay, and the way we work out the number of moles of acid that you have is you're going to have to work out the number of moles you started off with. Okay, so that's going to be the volume of the acid times the concentration of the acid. Okay, and the volume you're going to be using, of course, is your 10 divided by 1000, and the concentration will be from your previous titration, so 0.106. Okay, and if I get my calculator out, that will be 10 divided by 1000 divided by 0.106. Okay, so that will give you 0.094 as the concentration of the acid, and then we have to subtract this value here. Okay, so then we have to subtract 0.0207, okay, which gives you, so 0.0207, which equals 0.074 moles of acid. Okay, so far so good. Now why is it you're subtracting? Okay, it's because the acid has now reacted with the I'm using the wrong equation. You've got HA plus OH minus going to A minus plus water. Okay, so the acid has basically reacted with those moles of hydroxide to give that mole of conjugate base. So there's still going to be some acid left over, and the acid left over is these moles here. Okay, we then divide that by the total volume, and we get the value of the concentration as being 0.063 moles per decimeter cubed. So we can plug these numbers in now. Okay, so now you've got 0.020. Well, I'm just going to put the ratio in there basically, rather than all the numbers. That gives you a ratio of 0.33. Okay. Now, if you do the corresponding equations for the other numbers, rather than going through all of them, I'll just put the values that I ended up with. So I end up with 0.98 for this one and 2.93 for that one. Okay, now I'm also going to use Nannerel's numbers here. So she got 4.16 for the pH of that solution, 4.60 for that solution, and 4.88 for those solutions. Okay, so now with those numbers, we can determine the associated KAs. That's the next step.